In this lesson, we're going to continue our creation of a binary search tree class, and we'll complete that class and test it by adding some data to the class and see how the data is stored by traversing the tree, the binary search tree, once the data is in the tree. So let's get started. We have our node class already defined. We did that in the previous lesson. So we're ready to move on to the binary search tree class. But we're going to do this in a little bit different manner than we normally define classes. We're going to declare the fields and functions of the class first, and then go back and flesh out their definitions after we've declared the different parts of the class. So we'll start out with our declaration, class BST. We'll create our private section first. Our first field, and the only field, is the root node. Next, we're going to declare a private search function, which will be called from a public search function, which we'll declare in just a moment. Next, we're going to have a search function that returns a pointer to a node. And you'll notice for both of these functions, the parameters are a piece of data and a pointer to a node. We'll explain how those work later. The next function is the preorder function, which is a means of traversing a binary search tree. That's followed by the inOrder function, which is yet another way to traverse a binary search tree. And then finally we have the postorder function, which is yet another way to traverse a binary search tree. So those are our private functions. Now we'll declare the public functions. The first of those is our constructor, which will take no parameters or no arguments, followed by the public insert function, which just takes one parameter, the data to be inserted into the tree. Then we have our search function, which also just takes one parameter, the data being searched. Then we have our preorder function, our inOrder function, and our postorder function. So at this point, let's go ahead and build the project just to make sure that everything will compile correctly. Make sure all of our capitalization is there. And so that went just fine. So now we're ready to flesh out some of these definitions, and that's going to be a little bit more involved. We'll start with the constructor. And notice how we write the definition. We start with the class name, followed by the scope resolution operator, which is 2 colons, followed by the name of the function. In this case, it's the constructor, so it has the same name as the class. And here all we do when we create a new binary search tree is set our root node to null to start out. Next, we're going to define the private insert function. And what we do here is we're essentially trying to decide where to insert data, and we do that by comparing the data we're trying to insert with the data that's in the current node, either the root or some other node farther down the tree. First thing we do is check to see if the data is less than the current node. If it is, then we have to make sure that the node to the left, which is the way we have to go, is not equal to null. If so, then we call the insert function with the data and the node to the left, like so. Otherwise, we're ready to declare a new node to the left. So we create a new node with our data, and then we set the left pointer of the new node to null and the right pointer of the new node to null. So that's what we do if the data we're trying to insert is less than the data stored in the root node for all intents and purposes. Then, if the data we're trying to insert is greater than or equal to the data in the current node, again, more than likely the root node, then we check to see if the right child is not equal to null. If so, then we call insert with that node. Otherwise, we're ready to create a new node to the right. So we do the same thing we did when we were inserting a new node to the left. So we create a new node, and then we set its left and right pointers to null, like so. Close off the else if, and then close off the definition. Now let's write the definition for the public insert method. It simply takes the data we're inserting as a parameter. And here we check to see if the root node is not equal to null. And if so, then we insert from the root. Otherwise, that means we have a new tree. So we're going to set up the root node by putting data in the node and then setting its left and right pointers to null. Next we have the search function. This of course is the private function definition. So the first thing we do is we check to see if this current node is null. If it's not, then if the data that we're searching for is stored in that node, and we found what we're looking for, and we return that node. If the data we're searching for is less than the data stored in the current node, then we're going to return a recursive call to the search function moving to our left, since that is the way we move through the tree for data that's less than the data that we're searching for. Otherwise, if it's not equal to or less than, then it must be greater than, so we move to the right. And then if it's none of those, then we return null because we couldn't find the data at all. Now we'll define the public definition for search, which just takes one parameter, the data that we're searching for, and it returns the private version with the data that we're searching for and the root node. Now we're ready to define the functions for traversing the binary search tree. So we'll start with preorder. We'll define the public call first, and it calls the private method with the root node as a parameter. So here's the definition for the private function preorder. First, check to make sure that the current node is not equal to null. If so, then write out the data stored in that node, and then recursively call preorder with a node to the left. And then after that's finished, recursively call preorder with a node to the right. For inOrder, we'll do the public first. It simply calls the private version with our root node. So our private version looks like this. Again, we check to see if the current node is not null. If so, then move to the left. When you've reached the bottom, display the data, and then move to the right. And then last but not least, we have post order. So we do the public definition first, and the private definition will look a little strange. First, of course, we check to make sure that the current node, or most likely the root node, is not null. If so, then move to the left first, then move all the way down to the right. And again, we're essentially storing up node data. And then when you've gone all the way to the right, then we unwind the recursion by printing out all the data, just like so. So that wraps up our definition of the binary search tree class. Let's build and make sure we don't have any errors. There's a simple little typo which we'll fix. That's why we build first. Let's try it again. We left out a parameter there, so we'll add that in. And there we go, all the way through. So now we're ready to write a program to test our binary search tree class. So let's come down to int main. We'll create a binary search tree. We'll call it btree. Notice that we set it up as a pointer. Then we're going to insert some data, and we're going to insert a few pieces of fruit in here. We'll do apple, and then mango, and then a kiwi. And we'll display the tree in preorder form first, then in inOrder form second, and then in post order form last. This time we'll try to build and run, and everything worked fine. So our preorder shows apple, mango, kiwi, exactly the way we entered it in. The inOrder shows it in alphabetical order, apple, kiwi, mango. And then post order shows it exactly opposite of the way we entered the data: kiwi, mango, and apple. So with that, we have demonstrated how to define a binary search tree, and we've demonstrated how data can be inserted into the binary search tree once it's created and then displayed. And with that, we're finished with this lesson.